In this segment, I want to talk about an important idea when discussing waves, and that is intensity. Intensity is really the appropriate measure of how bright or how intense a wave is. Let me show you what I mean. Here I have an 18-watt light bulb. How bright is an 18-watt light bulb? Good question. Well, if I hold it right up to the camera, it's quite bright. Right? Oh, it kind of hurts my eyeball if I hold it right up to my eyeball. Oh, I can't see. It's very, very bright if I'm real close to it. But what if I take it over there? Well, I took my 18-watt light bulb over in the corner, and it's real dim over here now. So how bright is an 18-watt light bulb? Yeah, it depends on how powerful it is and how close to it you are. Combining those two ideas gives us the notion of intensity. The intensity of a wave, then, is really the appropriate measure of sort of the human experience of a wave. It's not just the human experience. It tells us how much energy per area is carried by that wave. It's how intense. If I'm talking about a light, it's how bright is the light. And if I'm talking about a sound, we could think about it as how loud the sound is to me, where I'm at, right? It doesn't just depend on how loud the speaker is. It also depends on how close I am. It depends both on the power and how far away I am. Okay, well, we can define intensity then as power per area. And the units then just fall right out of this definition. It is watts per meter squared. So I've said it's a combination of how powerful and how far away I am. But notice distance doesn't show up directly in this equation. Well, in order to understand how distance shows up into this idea of intensity, imagine that I have a light and it's emitting in all directions, right? That light I just demonstrated, it had a sort of a shield behind it, so it was reflecting the light in one direction. But imagine that we have a light that's emitting in all directions uniformly. Well, let's slow time down and imagine we're in a dark room and we just turn that light on. Well, that light will spread out. In what shape? In what shape will that light spread out in? Well, it'll be a sphere, won't it? And this power then, it's spreading out in a bigger and bigger and bigger circle, but we still have the same amount of power, right? We've got, it's 18-watt light bulbs, say, and now we've got 18 watts, and if I'm very close to it, then that light is spread out over a fairly small circle, sphere. But if I get a little bit farther away from it, then that light is spread out over a much bigger sphere, right? And so we get the same amount of power spread out over a much, much bigger area. So the farther I get away from that light, well, the less intense the light is. So let's remember that intensity is defined as power over area. If I have a source that's emitting equally in all directions, then what shape am I smearing that power out over? Well, a sphere. And the surface area of a sphere is 4 pi r squared. And so we get this equation shown in the PowerPoint. Intensity is the power of the source over 4 pi r squared. And so this is the distance, this is the intensity if I'm a distance r from a spherical wave with power source P source. The spherical wave, again, that just means it's emitting in all directions uniformly. Now, to be clear, this equation is not different from this equation. Our definition of intensity is power over area. If that light is moving out equally in all directions, then we're smearing that out over a sphere. The surface of our area of a sphere is 4 pi r squared, and we get this equation here. Fairly straightforward idea. Intensity problems tend to be a little bit tricky. They require a little bit of practice. Here's an example. Suppose you are powering a spacecraft with a 1 meter squared array of solar cells with an efficiency of 12%. Above the Earth's atmosphere, where the intensity of sunlight is approximately 1,300 watts per meter, what's the maximum power you could get from the solar cells? Okay, well, let's just set this up. Let's start with our basic equation. Intensity is equal to power divided by area. So let's see how much power is striking the solar cells. Well, first we'll solve for power. In this case, I've given the intensity as 1,300 watts per meter squared. times the area, which is 1 meter squared. I can do that multiplication problem in my head. That is 1,300 watts. But it's only 12% efficient. And so how much power do we get out of the solar cell? Well, that's 12% efficient times 1,300 watts equals, got to run my calculator here, and that equals 156 watts. Great, that's enough to run a camera, some computers, something like that. Okay, let's look at that next question. I'm going to clean up my board. Okay, so we just discovered that we're going to get 156 watts out of this solar cell if we're using it near the Earth. Now let's say that the spacecraft went to Neptune. Neptune is about 30 times as far from the sun as the Earth is. So we should get a lot less power, shouldn't we? How much less? Let's figure it out. Now in this case, we're still going to be using this idea that intensity is power divided by area. But now what we want to do is we want to use power divided by 4 pi r squared. Why? Well, what's the source of our power here? It's the sun. And the sun certainly is a uniform emitter, right? All of the power that the sun generates gets emitted in all directions. Now, I could go and I could look up the distance from the sun that the Earth is, Earth-Sun distance, and I could look up the Neptune distance to the sun, and I could maybe even look up the power of the sun, or I could solve for it. That sounds like a lot of work. Instead, I'm going to let the algebra do the work for me. Since the source is the same, whether I've got my solar cells by the Earth or if I've got my solar cells by Neptune, either way, the source is the sun. And so what I'm going to do is I'm going to solve this equation for power of the source, which in this case is the sun. So power of the sun is I times 4 pi r squared. Now, this equation works whether I'm at Neptune or whether I am at Earth. And since they're both getting their power from the sun, I could set those two things equal to each other. So what I'm going to do is I'm going to write I Earth times 4 pi r Earth equals I Neptune times 4 pi r Neptune squared. Sometimes students get a little freaked out by this, but again, all I'm doing is saying whether I'm on Neptune or I'm at Earth, I'm getting the same power from the sun. So I'm just setting this side of the equation equal to itself, in one case evaluated at Neptune, and in one case evaluated at Earth. My 4 pi's cancel, and I can now solve for the intensity at Neptune. Not too bad. You know what we can do here is we can, let's put this under 1. Let's combine these just a little bit, right? So the intensity of Earth times how far Earth is from the sun, how far Neptune is from the sun, squared. Now, that means that the intensity of Neptune is 1,300 watts per meter squared times, well, now at this point, many of you might go look up how far Earth is from the sun, or how far Neptune is from the sun. But I've given you everything you need in the problem. Here we could just say, well, the radius of the Earth is what it is, and the radius or the distance to Neptune from the sun is 30 times that. So whatever the radius of the Earth is, radius of Neptune is 30 times farther. My RE's cancel, and I can run my calculator. I get 1,300 divided by 30 squared equals 1.4. So notice that the intensity drops off by not a factor of 30, but rather by a factor of 30 squared, or 900. So if we have 900 times less intensity, then by the time we make it to the power out of the solar cell, we're going to get 900 times less. Okay, so that's our intensity at Neptune. In order to see how much power we're going to get out at Neptune, well, we need to retrace the steps that we did in the first part of this problem. And we need to say that power out is intensity times area times efficiency. Our intensity is 1.4 watts per meter squared. We still have the same size of solar cell, and we're still 12% efficient. And so when we do that, we end up getting 0.17 watts. Okay, is that enough to run your computers and your camera? Maybe not. You might need a bigger solar cell for that. We're getting 156 watts on Earth, 0.17 watts at Neptune. Notice that since the intensity was reduced by a factor of 900, the power out of the solar cell is also reduced by a factor of 900. So we could have just divided this number by 900. We kind of took the long way just to demonstrate how all these things work.